Welcome to this part 3 session on data encryption standard, the DES. In this session, we will encrypt the plain text and build ciphertext using the 16 subkeys that we have derived in part 2. We assume that you have already viewed our earlier two parts, else you will feel discontinuity in following this tutorial. Please download the Excel workbooks from the address given below. There are no macros in that Excel workbook. We have used regular formulae and functions only. In the DES algorithm workbook, you'll find 7 sheets. In this session, we'll spend more time with encryption and keys sheet. In an encryption process, we feed a key and a plain text into an algorithm of our choice to get a coded output called ciphertext. Here we use DES algorithm, and so we try to understand the working of the DES box. What do we do inside the DES box? We combine the two basic encryption techniques of confusion and diffusion by using substitution and permutation tables. Here we have the set of 16 subkeys that we have derived in part 2. They are available under the keys sheet. In this part, we have 4 permutation tables and a set of 8 substitution tables. Their contents are sacrosanct and cannot be changed. We use them as they are, whatever might have been the logic that had gone into building them. Permutation, as we all know, is rearrangement of the existing bits into new order as given in the relevant table. We have 4 permutation tables: the IP table, the EBIT selection table, the PBIT table, and the IP inversion table. In row 2, we have copied the contents of the IP table. In row 3, the values from EBIT table. In row 4, the values from PBIT table. And in row 5, we have copied the IP inversion table contents. These values, because they are unchanged, and whenever we need to use them, we use HLOOKUP function. The 8 substitution tables are available in the lookup sheet. Let us check what is inside the DES algorithm box. We begin with IP permutation, then move on to the 16 rounds of Feistel network. Row 6 contains the plain text. This value is what you have entered in the summary sheet. And is copied from there. Don't enter any value here. Again, this plain text is converted into binary in row 7 using VLOOKUP formula. This binary plain text is permuted using IP table using the HLOOKUP. V2 contains IP table, and this is my range. We split the row 8 into 2 halves. The first half is placed in row 9 and the right half is placed in row 10. The naming convention is L0 and R0. Please follow this subscript closely until we complete the entire 16 rounds of encryption. We are now ready to enter the first round of Feistel network. inside each Feistel round, we have the IP permuted L0 and R0 in rows 9 and 10. We begin with L0 but leave it as it is until we consider it for XOR in step 7. Next, a copy of R0 is stored in L1. This is one of the outputs of this round 1. We use same 32-bit R0 and permute with E-bit table. The output now is 48-bit long. XOR this 48-bit output with the subkey K1. We use key K1 because this is round 1. This 48-bit output is split into 6 bits each and its value is taken from the substitution tables. The output of the substitution table is permuted using the p-bit table. XOR the output of the p-bit permutation with L0 that we have kept aside in step 1. This output is our new R1. Notice we have already obtained L1 in step 2. This completes the mixer block of the Feistel network. We now store this R1 in L2 for use in the next round. This is a swapper block. Within one round of Feistel network, this is what happens. We are now ready to move on to round 2. Let us check the implementation of the above actions in our Excel sheets. Remember, we left off with L0 and R0 in rows 9 and 10. We leave L0 untouched until step 7. Copy of R0 is stored in L1 in row 11. Row 10 is permuted with E-bit selection table in row 3 and written in row 12. Notice row 10 was 32-bit but row 12 is 48 bits. Copy subkey K1 from the K sheet in row 13. Remember, we use K1 because we are in round 1. XOR row 12 and row 13 and write it in row 14. Excel does not have an XOR function. Our formula is equal to if cell 1 plus cell 2 equal to 1, then 1 L0. That is, if the bits are not the same, we store 1 as the result, else 0, whatever be the total. Now, we use values in row 14 and the substitution tables to get new values and write them in row 15. Let us understand the substitution operation in more detail. For substitution, the DES algorithm uses a set of 8 tables, S1, S2, S3 and so on. There are 8 such tables. The way to use them is to go row-wise, column-wise lookup. If you look at row 0 and if you look at column 10, you will get a value of 6 from S1 table. For the same row 0 and column 10, we get 2 from S2 table. So we must know which table to look for and pick up the right value. These values are used for substitution. The existing bits will be substituted with new values, which is for adding confusion in the process of encryption. Let's see how this works. Say, here we have 48 bits in row 14. We split these 48 bits into 6 bits each, and thereby we get 8 values. For the first 6 bits, the values have to be obtained from table S1, and for the next 6 bits from S2 and so on until we exhaust all 8 values. These are our first 6 bits. Consider the first and the last bits to get the row value. Row value here is 2, and in the next set it is 1. Now we consider the middle values. These 4 bits give you the column value. For the first set, we get the column value as 3, and for the second set it is 10, and so on. The values for all the 8 sets are tabulated. Now we know which substitution table to look into for each set, and we'll find the values. Let's go to the lookup page. For the first 6 bits, row value is 2 and column value is 3, and we get the substitution value as 8, which is taken to cell G15, and the binary is automatically replaced in the range C15 to F15. Similarly, for the next 6 bits, for row 1 column 10, we have the value as 1, which is taken to cell M15, and the binary replaced in I15 to L15. But for our present calculation, we have vertically transposed these 8 tables, and we don't even split the row and column separately. Instead, we take the entire 6 bits at a time and using the VLOOKUP function get our values. First 6 bits from our example is 100110, and we straight away get the value from the lookup range from cell W37. And we continue the same way for the remaining bits. So for each 6 bits substitution, we get a 4-bit value. You will notice the 48 bits that we began with have now become 32 bits. This is how substitution works. Row 16 is redundant in a way that we copy values from row 15 and write them in row 16 and put them together. Otherwise, row 15 and 16 are same. Permute this row 16 using p-bit tables and write in row 17. XOR row 17 with row 9, which contains L0. This row 18 uses R1. We started with R0 and now we get our R1 here. This completes the mixer block of 5-step network. From row 11 we get our L1, and row 18 gives a R1. These two are the output of round 1. Before we move on to round 2, we store this R1 into L2 in row 19. This operation is called swapping. The above set of operation is repeated 16 times. 2, 3, 4 and so on until we get L16 and R16 in rows 131 and 138. This L16 and R16 is arranged as R16 L16 in row 139. Now we apply IB inversion permutation given in row 5. Row 140 is our ciphertext in binary format, and row 141 is this binary converted into hexa using VLOOKUP function. Row 141 is carried to the summary sheet AK2 to AZ2. This completes the encryption process. In an encryption process, ciphertext should not show the original statistical structure of the plain text. We achieve this by using substitution and permutation. And how do we measure the effectiveness of the operation? Make a simple change of one bit to your plain text and see how many bits it has affected in the ciphertext. We have provided this in the avalanche effect part of the summary sheet A39 to BO46. Row 46 always contains the binary of the ciphertext in row 2 AK2 to AZ2. Before making any changes to the key or plain text, copy row 46 and paste special values in row 41. Let us change the final one in the plain text to 2. We are changing it just by one bit. The new binary ciphertext is automatically copied to row 42. The total number of bits changed is available in cell BO43 of row 43. We see 27 bits have changed. We have made a change of 1 bit and find that 27 bits have changed in the output. This is the way to measure the avalanche effect. Pastel networks are very appealing not just due to their simple design but also because the same hardware circuit can be used for both encryption and decryption. How? We will see it in the decryption video. We suggest that you work with various plain text and keys and get a handle on DES encryption using our DES algorithm.xlsx. Don't forget to revert to our test key and plain text before moving on to decryption. We will present decryption in part 4 of this tutorial. Bye.